So we are moving on to rotational motion. So we're in chapter 7, but technically we're on unit 8. So we'll just go ahead and get us started here. All right, so rotational motion is an important part of every day. You guys see it all the time. You just don't really notice it probably. But motion of the earth, obviously, rotating wheels when you get in your car and you drive or you ride your bike. And angular motion is going to be expressed in terms of angular speed or angular velocity, angular acceleration, and we'll talk about centripetal acceleration a little bit later. So we basically have new symbols for these things. So you guys already know what displacement, velocity, and acceleration are, but now we're going to have angular displacement, angular velocity, and angular acceleration. So angular displacement is going to be delta theta. It's a change in an angle. Angular velocity is going to be use that weird little W. And then angular acceleration is going to be our little alpha. So it looks like a little curly A. And we'll talk about how these are related in a minute. So the first thing we need to remember is what a radian is. We're going to probably have our calculators in radians most of this chapter. So the radian is a unit of angular measure and can be defined as the arc length S along a circle divided by the radius R. So theta is going to be S divided by R, and so that's how they're related. So comparing degrees and radians, so if you have 1 radian, in order to convert it to degrees, you would multiply by 360 over 2 pi, which is technically just 1. And if you wanted to convert from degrees to radians, you would take your theta. So here's basically the formula. It's saying the same thing as above. So basically what they've done is now you're going from degrees to radians. So if you want radians, you're going to do pi over 180, which is really just 2 pi over 360. They just divided both top and bottom by 2. And then you're going to multiply by the degree. So I think you guys can figure that part out. So when something spins, we say that it spins around the center of itself. So the axis of rotation is then the center of the disk. If we need a fixed reference line in order to figure out the change in theta, we just make a reference line, and then however much, whatever theta that reference line moves, that's how much the disk is moved, or any point on the disk. And so theta is going to measure the angular position. The definition of a rigid body, which we are going to be using rigid bodies throughout this chapter, is that every point on the object undergoes the same circular motion about the point O, which is basically just the center. So that just means that all the parts of the body rotate through the same angle during the same time. So it's considered to be rigid because every part of its body is fixed relative to the other parts of the body. So you're not going to have the inside part going faster, sorry, not faster, but moving through more angle than the outside part. They're all going to stay within the same relative position of each other. So angular displacement is defined as the angle through which the object rotates in some time interval. So basically if you have, you're originally starting at, at point A here, then your theta initial is here. And if you were to move from point A to point B, then your change in theta would be this little piece, which would basically just be theta F minus theta I, which would be your change in position. So we'll start to develop some equations here. The average angular speed, omega or W of a rotating rigid object is the ratio of the angular displacement to time. So it's the same thing. It's the change in position over time, but now we have change in angular position over time. It's the same thing as V equals D over T. It's the exact same equations, just with new variables. So just like before, the instantaneous angular speed is defined as the speed at any given second, the angular speed at any given second. And we're going to consider that speed will be positive if theta is increasing counterclockwise, and it will be negative if it's spinning clockwise. So when the angular speed is constant, the instantaneous angular speed is equal to the average. All right, so moving to angular acceleration, you guys should be able to guess this equation, but it should be the change in velocity over time. So if we're talking about angular acceleration, we're going to be talking about angular velocity. So we're going to be talking about that omega or that little W. So it should be the change in angular velocity over the change in time. And again, we're using this cute little fancy A. So the units for angular acceleration are going to be radians per second squared. For velocity, it would have been radians per second. For position, it would be radians. So positive angular accelerations are in the counterclockwise direction, and negative accelerations are in the clockwise. And when a rigid object rotates about a fixed axis, every portion of the object has the same angular speed and the same angular acceleration. So I'm not picking one point on the circle, where they're all the same. The tangential or linear speed, that's the same as just our regular velocity. We use V to stand for it. So sometimes they'll call it tangential, Sometimes they'll call it linear. It's the same thing. It's just our normal speed. And our normal acceleration will depend on the distance from a given point. So again, just like with velocity, the instantaneous acceleration is going to be defined as the angular acceleration at any given second. Same as before. Okay, so this is probably one of your most important slides for the chapter. Basically what's happening is they're giving you the kinematic equations that you used to have right there. And they're basically showing you that the new kinematic equations you're going to use are going to be exactly the same, except for wherever you see v, you're going to put omega. And wherever you see delta x, you're going to put delta theta. And wherever you see a for acceleration, you're going to put alpha for angular acceleration. So they're the exact same equations, the same 4 equations, and we can use them the exact same way. They're just with different variables. And so there should be one more there. I think we used one more, so you can convert that one as well into angular. But they're literally exactly the same thing. So you're going to use them the exact same way that you used these kinematics, the linear ones, before. Here's a few other helpful relationships. So displacement we knew was the arc length divided by the radius. The speed, the tangential speed is going to be equal to r, the radius, times the angular speed. And the acceleration, the tangential acceleration or the linear acceleration is going to equal the radius times the angular acceleration. So those are going to come in handy. So keep those ones close. Okay, so I apologize. Something happened to this slide, so the example looks a little weird, but I know what it says, so I'm just going to go ahead and read through it, and we'll go through the example. So it says a compact disk rotates from rest up to an angular speed of 31.4 radians per second in a time of 0.892 seconds. And they want us to find the angular acceleration of the disk. So we're going to do that first. So let's go ahead and write down our variable. So they told us that it starts from rest. Whoops. So I'm going to use my W initial is going to be 0. My W final is going to be 31.4 radians a second. We're looking for alpha. And they gave us the time of 0.892 seconds. So really I'm just going to look at my kinematics, and I know they're not up here, but you guys should have them in front of you. And we're missing delta theta, remember that whole technique? And so we're going to use this equation. So omega final minus omega initial plus alpha theta, we'll just plug in. And if you do that, you should come up with the fact that alpha is going to equal, let's see, 31.4. I'm sorry. That's the wrong one. Not 31.4. Should be 35.2. And units are radians per second squared. So I went ahead and I opened up a new slide so we'd have room. So part B of that question asks, through what angle does the disk spin during this time? So they're asking us for displacement. So we already have every other variable that we need, so we can just use the easiest equation to find displacement. So I like this one, but it really doesn't matter which one you use. So if we plug into that one, we have final, which was the 31.4, initial was 0, and time was 0.892. And so you'd come up with the fact that the delta theta would be 14.0 radians. Part C asks us to figure out what the tangential speed would be at 0.892 seconds. So that would be the final speed converted into the tangential. So we have final speed at that time. Our speed was 31.4. That was the angular speed. And if we want to convert that, we're going to have to use this tangential speed equals r omega. And so if we do that, we do the radius, which they told us was going to be, let's see, 4.45 centimeters, so 0.0445 times 31.4, and if you do that, you end up with 1.39 meters per second. So turns right back into meters. And then the part D, they're asking for the tangential acceleration or the linear acceleration, so we can just do the same basic thing, where A equals R alpha. We know that R is 0.0445. We know that alpha is 35.2. And if we multiply those, we get A to equal 1.57 meters per second squared. So that's it. That's all you have to do. So it's basically like the old kinematics, except with just different variables.